Sorry about that. We'll be discussing this paper, Comparative Document Summarization via Classification. And to start off, we'll define what the problem they're trying to solve is. Document summarization really has different flavors. So the most generic form is like, I just want to see a small summary of what the document is. So maybe you have a news document, newspaper article, and you want to know what it says in 3 sentences. That's the first version. That's generic, too long didn't read kind of a thing. Query-based document summarization is basically when you like put in a query into a search engine and they want to return to you a snippet which kind of summarizes the page and also shows you where in the document the different keywords occur. So that's like query biased. What we're going to discuss today is comparative summarization, and that's when you have a group of documents that talk about more or less the same thing, and you want to find documents that are sort of prototypes and describe the whole document group as a whole. Update is somewhat similar to comparative, where you're like you have a news which is developing over time, and you want to have a storyline. Say, for example, uh, the Golden State Warriors were down by 17 points yesterday, and then they won. And you really want something that summarizes that storyline of events. So it's detecting what changes in a particular group of documents over time, and then creating a summary of that. But we really want to care about comparative document summarization. So the main idea, as I said before, is finding one or more representative documents from a set of documents. These documents should really have like 3 main properties. Uh, it should be selected documents should cover the topic that that group of documents talk about. The selected documents should be diverse from each other in that they shouldn't talk about the same thing every time. It should focus on different parts of it. And they also should be different from other document groups or prototypes of other document groups. So for example, if we go back to when Obama was president and he gave out his inaugural speech, it focused on many different aspects. So some focused on his like plans for healthcare, some on his plans for economic growth. Whereas if you have a generic document summarizer, it will probably focus on the things that are common in all of them. But comparative document summarization, you really want to focus on things that are diverse and that tries to capture all the different types of information that's there while also providing the main idea of the group. So that's the problem we are trying to tackle. So here's an illustrative example as we saw in the paper. So on the x-axis we have time, and we have 6 different news outlets, and all of them are reporting about artificial intelligence, and more or less they're about the same, but there are differences in the things that get reported, and we really want to find what those diverse sets are. For example, if we look at news media outlet, um, the first 4 articles in Feb might have been about the same specific thing, so they just selected one. In March, there might have been a shift in paradigm, and they maybe started reporting about something else, and we want to see that change. And overall, when we are looking at the summaries, we should be able to say these summarizes the ones from this time group, whereas these documents summarize it for this other time group, and they should be distinguishable to a human. Like here, the division in the grouping is by time. It can be by any other things. For example, whether the opinions are left wing or right wing, something like that. So what are the ideal properties that this should have? So the first property they talk about is coverage. They want the ideal prototype should have more or less good coverage of all the different aspects that are discussed in the group of documents. For example, if we go back to the Obama example, um, all of them should really, like prototype selected should really have convey the idea that they are summarizing uh, Obama's inaugural speech. Um, they should also be diverse, like we mentioned before. So if one talks about the health if one of the prototypes selected talks about his economic aspects, the other might talk about his international relations or something like that. So they should be diverse as well, and it should discriminate against prototypes that are selected from other groups of documents. So these are the three main properties that we want. So we go into a problem definition. So let us say we have a set of G document groups, x1, x2, .xg. Each group has ng number of documents, and that's xg, small g. And the goal is to find x bar g, where x bar g is a subset of m documents from xg, such that it is represents the properties like coverage, diversity, and discriminativeness. Sorry. Okay. As the title of the paper says, we are trying to do this using classification. And so for coverage, we define this as an ideal classifier should not be able to distinguish between the prototypes and the document group of which it is a prototype of. And for the discriminativeness, we should be able to say that an ideal classifier should be able to perfectly classify prototypes of one group from documents from all other groups. That's the main idea of the paper, and they summarize it here. So let us assume that there exists a classifier for which accuracy of classifying two different classes x and y is given for those two classes. Accuracy of x, y is the accuracy of the best classifier that can distinguish between two classes x and y. And if we assume that, then the problem state that we stated before kind of boils down to these two terms. We are trying to maximize over all the groups the accuracy of the negative of the accuracy of xg bar and xg, which means we are trying to.
I had a question. I just want to make sure I got the notation right. So
sure.
xg with the bar, that's the prototype, and then xg without the bar, so that's summing over all of the different.
It's just the set of documents. So
okay, all the documents.
Yes. Sorry. Yes. So xg is all of the documents in that particular group.
Okay.
We aren't trying to like automatically divide them into groups. We just assume that the groupings already exist.
Okay.
Yes. So should have mentioned that.
Thank you.
Yep. So yeah. So we are trying to sort of maximize the error of the first classifier, accuracy of the first classifier, and we are trying to minimize the error of the second one. Notationally here, this basically means x not g, so where this does not belong to any of the, x not g is basically all documents from groups that are not g, and we want to maximize, minimize that error rate over there.
Just to clarify, I think those
yes,
subscripts should be lowercase g's.
Yes, that should be true. Yes.
Could you say that again, please?
These should all be lowercase g's. That's just a typo I had there.
When you point out the notation, could you also say them like where they are? Because
okay,
I won't be able to see them.
I see. So when we say negative of accuracy of x g bar, that g should be small g because we are summing over all of them. We're not considering the whole thing as a. Yeah.
But if that's small g, then how are you finding the accuracy between? Like, what are you trying to get the accuracy between if you're going to be?
We are trying to get. So, like I mentioned before, the groups are separate sets of documents. We don't really have to demarcate the group separately. What we really are trying to do is over the different groups, we kind of want to find the accuracy for each group. We have a document, and so.
Because this now saying what is the accuracy of this document belonging to this group?
Yes, so this group XG capital would be
the group.
Yeah, so this one particular group here, but where we really want to talk about these individual groups. Yeah.
It's individual groups within a subset of
group.
yeah,
Okay.
bigger group. Yeah.
Subset of documents.
Yeah. Sorry, it skipped. Yes. The first approximation of the accuracy we do is using the nearest neighbor classifier. It's basically pretty simple. We select each of the prototype documents such that a similarity function is maximized. So just if there's m documents, you have 2 to the power m different subsets for, oh sorry, and choose m different possible subsets of m prototypes. You just find which one of them is the most optimal, and there are different ways of doing that. Similarity function can be anything really. Negative of distance is the one that they mentioned in the paper. One drawback is that obviously the one term that we saw here, the accuracy of the classifier that's trying to distinguish between the prototypes and all other documents not in that particular group, we kind of ignored that. And then the other main concept that is introduced in the paper is maximum mean discrepancy. Uh, at a very high level, we can sort of think as MMD as the difference between two probability distributions. So let's say xg bar is a random variable that denotes what the uh, what the prototype document is, and xg is the random variable defining uh, the group that that it is a prototype of. So we kind of want to minimize uh, uh, the difference, the discrepancy between these two, so that like the prototype and the group of which it is a prototype of doesn't have a lot of discrepancy. And then the intergroup discriminativeness, it's sort of the same idea. We have xg bar as one of the prototypes of a group G, and x not G as as all the other documents. So kind of want to maximize that one. Maximize the discrepancy between that one is because if the discrepancy between that one is more, a classifier will be able to classify it more accurately. So we do go into a little bit of a deep dive into maximum mean discrepancy, and the way it's defined is the supremum of the difference of, uh, sorry, the two probability distributions P and Q over a function space F, where it basically means you are trying to find one function F such that the the expectation P of Fx and expectation Q of Fy, this is maximized. Um, this is kind of an intractable problem, but if we assume the family of functions f to be a reproducing kernel Hilbert space, which we have defined there. It has some nice properties. So the reproducing kernel Hilbert space basically says a reproducing kernel Hilbert space has two properties there. So k of xy is a kernel function that calculates the similarity between x and y, which is also the dot product of phi of x and phi of y, where phi is the function feature map that maps x to the required space. And the reproducing property, the one that we're really interested in here, is that phi of x over a feature map f actually gives you f of x. So this is a property of reproducing kernel Hilbert spaces, and more information can be found in math books, which I did not read and I will not go into. But basically, if we assume those definitions, we can reduce the above the definition of MMD over PQ and F into uh, this. So we say EP of Fx, we can use from the second formula and write it out so that it becomes mu of P, like the dot product of mu P and F. There's another typo there. It should be P, not bracket. Sorry about that. So we kind of reduce this problem to the Hilbert space norm of mu p minus mu q. And using the triangle inequality, we can take the square over the Hilbert space. So F is now the Hilbert space. So that gives us this expression, expectation of k of x comma x bar minus twice expectation of k of x comma y and plus of expectation of k of y bar. What this lets us do is it lets us define MMD using kernel interactions of documents without having to calculate the underlying distributions or go iterating over the space of functions, which is a pretty difficult task. Sorry. Using that, we kind of come here so we replace MMDs, the expectations in MMD using sample means and using sample means because we have documents, we don't really have to use samples there. We don't really have many other options without really complicating it further. The kernel function used in the paper was a Gaussian kernel with gamma greater than equal to 0 as one of the hyperparameters. So one good thing about MMD is that it also introduces diversity. So if you remember using this expansion, so in the formula of MMD square, we have one term that would come out as expectation of k of xg bar comma xg bar prime, which is basically measuring the similarity. So kernel of xg bar and xg bar prime measures the similarity between the prototypes, and maximizing the negative of this would increase the diversity. In the term udiff that was defined for the first one, this actually comes out with when we expand it, there's a constant of lambda minus 1 attached to this expectation, and since lambda, we usually take lambda between 0 and 1, so it's kind of taking away a bit from the whole optimization problem. So we can remove that. We can also remove all the terms which does not have xg bar in them because they are not really related to they're constants in this respect. So you can have a much better optimization function udiv, which is basically the first term stays intact, and we add a second term which is basically the only term which deals with xg bar and x naught g and is the intergroup discriminativeness. So ultimately, we have three optimization objectives: UNN, UDIF, and UDIV. And with that, we go into optimization. So there are two different optimization methods that were introduced in the paper. First is set utility maximization. So going back to set theory, we have omega, which is the power set of S, so the cardinality will be 2 to the power S. So if we have defined a function f from 2 to the power of from omega to r, where r is the set of real numbers, this f is basically measuring the goodness of badness of a particular subset belonging to omega, and this function f is submodular if these particular conditions are fulfilled. So assume you have x and y, which are two different subsets belonging to phi. X is also a subset of y, which basically means the cardinality of x is lower than cardinality of y. Let us assume that there exists an x which belongs to the difference of the sets s and y. So it's basically it's not in x or y, but it's in s. And if we calculate the function of the increase in utility of f, or like the value of f of x, by adding x to either of the subsets, adding it to x should have a greater increase than adding it to y because x is a smaller subset than y. And this is called the property of diminishing returns. As you get larger, as the subset you're considering gets larger, the amount of uh, gain you get by adding a new prototype to the subset decreases. And it's monotone if for given x and y, given subsets x and y, if x is the cardinality of x is greater than the cardinality, sorry, if the cardinality of x is lesser than the cardinality of y, f of x should be, uh, sorry, there's a little mistake here. So if cardinality of x is greater than the cardinality of y, then f of x should be greater than y. So basically it's saying that doc, uh, by adding a new element will never have a lower, so it's like a lower utility score. So it's always increasing monotonically. So that's how they define monotonicity. And this is a result from mathematics, and which says that if this utility function is selected to be such that it's submodular and monotone, utility maximization can be done with an approximation guarantee of 1 minus 1 by e, which means if the best score that you can get is 1, you'll have at least a score using greedy maximization. Using greedy maximization, you'll have uh, at least 0.63. And that's what they do here. So they have an algorithm to greedily maximize the set utility. Here u is any one of the three objective functions. It basically says we take all the groups, we select, we assume that we have m prototypes from each. We take one example that is not a prototype yet, and we go and see how much it increases the scores by. If it's the maximum, we add it to the set of prototypes, and we iterate till we have reached m over all G groups. Yes, so the few things here that's worthy of mentioning is that the nearest neighbor utility function is submodular, and it was proved by Wei, Iyer, and Bilms in 2015. MMD square is generally monotonic, but the U diff, which is a difference of two MMDs, is not monotonic in general. But it was shown that even if it is not submodular monotonic, it still has a high probability that it will give you a more or less good result, and the experimental results actually show that. UDiv, however, is submodular by some property of submodular functions, which I do not understand. They also optimize using gradients. The problem about using gradients in this problem is basically you're trying to do a selection. So you can't. So it's a discrete space. You can't do gradients. The easiest way to deal with it is just relax the requirement that xg has to be from the document set. We just calculate a set of optimal ag bars, and then snap it back using closest like distances. So that's basically what they're saying in the last line there. Calculating the gradients, it's actually pretty simple. Sorry, I copy pasted it here. It was too big. It's pretty simple to differentiate because K is the RBF kernel. So the derivative is basically the RBF kernel with whatever's inside it. So you get force gamma by mg outside, and then the rest of it is kind of the same. This is the derivation for MMD of AG, AG bar comma XG. You can do the same for AG bar for X naught G. And the optimization algorithm used was LBFGS. Moving on to the data sets that were used for the test. We have two types of data sets. One is a set of handwritten digits. It's from USPS, the United States Postal Service. So it's like about 1,000 handwritten digits in grayscale, 16 cross 16. They kind of reduced it to 39 dimensions for some reason, and They use the training and test set splits and stuff. For the other part, the real world data set, they collected news articles from Twitter. So they created a bot that monitored Twitter, and whenever it saw a news link related to something, it went in and fetched that. So they used a technique called snowballing, which is basically saying I'm going to start with a keyword set of K, and when I get a new document, I'm going to extract the most important keywords from that using some method and add those new keywords to the keyword sets of that we're already tracking, and they kind of just continued using that. They collected news articles about 3 different topics over about 12 months, and they report results on that.
So before we take a break, were there any questions? I'll ask a question. Can you go back to the slide that introduces the submodular functions, please? Is after the derivation. Yeah, I guess, can you just reiterate again the significance of submodular functions? Also what they were. So, maybe I wasn't paying attention, but.
Yes. So in general, the submodular utility maximization problem is like you have 2 to the power n subsets where n is the cardinality of the set S. And so to find the optimal subset is like exponential space problem. In case the function f is submodular and monotone, you can have a polynomial time approximation of 1 minus 1 by e in polynomial time. So that's why we need to try to prove if the utility functions we have are submodular or submodular under certain conditions, or at least close enough that it still has a bit good enough approximation.
Okay, that makes more sense.
Yeah.
Quickly go to the slide about the optimization algorithm. No, next couple of slides. Next. This one. So basically, you mentioned that the space is discrete, but you're still using a gradient-based algorithm, right?
Yes. So, sorry, I have no idea why that keeps. Yeah. So what we do is we relax that constraint. We say this xg, where x is basically a representation of a vector representation of the document. We say that that space is not just a few elements. We just say it's a continuous space. So we calculate the most optimal set of prototypes from that set, and then we find the closest for each of the optimal prototypes that we calculate. We find the closest actual document in the set.
Metric or something.
Yeah.
Okay.
It's this one.
Oh, okay.
Yeah.
What was the comment that you referred to?
So the question basically was, since the utility functions are discrete, how can we do the differentiation? That's the gradient, that's the stuff, data set, and
Oh, okay, let's take a quick break then.
I have.
Oh, never mind.
Can you explain a little bit how did they get the representation of each document?
Oh,
because
sorry,
I guess
I
you
missed that.
skipped a little bit. Yeah.
Here.
Yes. Okay, so the handwritten digits, I believe I went over. The news data set. So they kind of didn't really focus too much on the document representation part, and this is one of our discussion points actually. So what they did was they took each news article, took the title and the first 3 sentences, and they averaged the glove embeddings of all the words in there, and they call it the approximation for a document. Could it be better? Possibly, but that's what they went with. So we go into the result. Oh, wait, am I supposed to start? Okay. So we start the evaluation. So they compare 6 methods. They have 6 groups of methods. So they compare. So we had 3 different objective functions that we defined. So first one was nearest neighbor. So they use just the greedy optimization for nearest neighbor, and the method is denoted as n and comp greedy. For mmdiff and mmdiff, they do the optimization using both gradient optimization and set greedy optimization, and they are called mmdiff greedy or grad, and same on mmdiv greedy or grad. We are comparing these against three baselines. So k-means is basically we have a group. We're just going to find the find m, where m is the number of prototypes, which is a parameter. So we're going to find m cluster centers, and we're going to find the closest document to that cluster center. It's the same as with AG. They've used the same formula to find the prototypes once the cluster centers are done. K-medians is very similar to K-means. The only one significant difference is that the output of K-medians is actually points that are in the set in the data set. So we don't really have to focus on the finding which document is the median, is the prototype. It's just the cluster centroids returned. And the final and the most important baseline here is MMD critic. This was published a couple of years ago, and this uses MMD to find both prototypes and critics. So critics is basically defined as prototypes, which like as examples which are in the group but most different from prototypes. So for if we think of the USPS digits example, it might be a 0 that really looks like a 6 or a 9. So those are critics. And the way they calculate the prototypes is basically they just take the uh, the prototypes calculated by MMD critic as is. So we have two different evaluation paradigms here. The automatic evaluation paradigm basically focuses on the idea that if we just had the prototypes, how good would a classifier be able to classify uh, the groups based on training on just the prototypes? So the authors kind of like found prototypes. They found prototypes where m was set to 2, 4, 8 or 16. So basically they're saying you're going to find 2 prototypes for each group, 4 prototypes for each group, or like 8 or 16. They generate a cross validation set. So yes. So for the news topics, like they say, they create 10 random splits, 80% training, 20% test. So this is kind of an interesting division. So they're not like dividing it into splits, but what they're doing is they're randomly sampling the whole set and dividing it into 2 groups. So it's not necessary that this like splits are uh, exclusive, like mutually exclusive. So it's the same thing, which is like 80 and 20% split. So they're doing it randomly 10 times, and they do it so that they can calculate uh, confidence intervals. And even for the image data set, they have the same method. Uh, the evaluation kind of looks hard to read, but okay, so on the left-hand side, we have uh, one nearest neighbor classifier, which is trained on the prototypes and then sent out. And on the right, we have SVMs. On the bottom, we have the number of prototypes used, so 2, 4, 8, and 16. We have the different data sets on the right-hand side, and the bars represent the accuracy. It's a lot of different dimensions. And it's a little hard to see, but basically it's the ones on the right are the methods that were defined using in the paper. Uh, there are some basic general trends, I guess. So the first thing is as the number of prototypes increase, accuracy of the classifiers generally increase. Um, Overall, and it's very hard to read from this, but in 22 out of 24 evaluations, so like it's like 3 different data sets. Uh, sorry, 4 sizes of prototypes and 2 different classifiers. So we have 24 combinations. In these 24 combinations, in 22, the proposed methods were significantly better using the one-sided sign test. with a p-value of less than 0.5. In the other two, k-median was better, but there was an overlap of confidence intervals, so it's not significantly better. On the other hand, and this is the unfortunate part, is that even though the proposed methods are better, there is no one clear winner among the proposed methods. They're all like, they're usually better, they're usually all good, but there's no one clear winner that's like MMD diff greedy is the best. We really can't say anything like that. Um, but in 15 cases, the gradient-based optimization performed better than the greedy ones, even though there were no guarantees for the greedy ones. I'm sorry, the gradient-based ones. And they also perform a user study. The user study, okay, so this was really confusing to read from the paper, but the gist of what they are doing is uh, we have they're taking one of the news topics. The topic was beef ban. Um, it was from, I believe, July of one year to June of the next year, or June of one year to July of the next year for a total of 14 months. So what they did was they divided the data set by month and created combinations like pairs of each. So December of 2017 and February of 2018 is one pair. And what they do is they did the automatic evaluation as defined in the previous section for all of these different pairs of uh, splits, time-based splits that they created. And based on the results, they selected the top 10 best performing pairs for each of the 4 different methods that we are comparing, which are k-means, nearest neighbor greedy, MMD diff greedy, and MMD diff grad. They selected these 4 because in general these work better. Um, what the study participants were given was an interface like this, where they were given an overview of what the topic was, and they were told that the 2 groups were news articles from 2 different time domains, and they were asked to like decide um, which time domain a given prototype was from, and the prototype was selected from one of the methods. Sorry. Yes. So the prototypes were selected using one of the 4 methods that were being evaluated, and we calculate the accuracy of the human at classifying which times period the prototypes are from. This basically is trying to identify whether the summaries that are generated have enough information that a user is able to tell which group they're from. So it's kind of the discriminativeness that they're testing, as well as I don't know how they're testing coverage using this experiment, but at least it's something. These are the results. So the first one, A, it has the balanced accuracy. So balanced accuracy is basically the macro average, I believe. So they calculate the average for each class and then just average they calculate the accuracy for each class and then they average it. And whereas the plain accuracy is basically TP by P plus TN by N. There's a difference because one captures, so if you're calculating TP by P plus Tn by N, so if there's a dominant class and the results are good for the dominant class, the result for the dominant class will kind of dominate. Yeah. These are the results. So, yeah. So, sorry, need to take a look. Yes. So B gives us the automatic classification results. So it's the same paradigm as before. C is the accuracy of the users. Um, each bar represents prototypes from one particular method. Diffgrad seems to work better for in most cases for this. And the green line on the first on the first image, on the first graph A, gives us the average accuracy of an SVM trained on all possible um, documents. So trained on XG as opposed to X bar G. These are the results. Yeah. Discussion points, as we mentioned before. Obviously, the document representation. Uh, it could be better. I mean, if we are just using the first three sentences, you're probably losing some information. They also don't talk about how much they're actually doing, like what kind of pre-processing they're doing. But one point against this discussion point can be that all of their evaluations, they're comparing against the state of the art, which is MMD critic, but they're using the same data set. So it still has the same even playing field so that they can compare their proposed method with the state of the art. So we can still say it's better than MMD critic and their method in general works well. We just can't say whether this is the best method to calculate or the whole pipeline, whether the whole pipeline is the best way to calculate comparative summaries. Maybe we can change the first part, which is the representation part, to get it to work better. Um, Another important point, this is more of a thing that I'd have liked to see. What other ways of dividing the two documents can this really work well on? Um, Time is the one that they focused on. We could focus on something else, like whether it's right wing or left wing, or whether it's about uh, a particular player, if it's positive or negative, or any other kind of thing. And that'd have been nice to see. Um, these are the references. Uh, Questions?
So I guess we could thank you because you're kind of at the end, but then we'll go back to discussion. So yay. Anyone have comments or questions to clear up before we get onto the discussion?
So you said that this compares against the state of the art in terms of just how it uses just the title in the first three sentences.
Yes.
And that was enough for it to actually.
So it's good enough to differentiate between this current state of the art. So if this representation of documents is bad, it's bad for all the methods that are being compared. So when we are comparing and we are trying to say X is better than Y, under these conditions, it's true. So we can't say whether or not this is the best method for actually performing this task. But if we are comparing just the objective functions they defined and the objective optimization methods they came up with against the state of the art for doing the same, it kind of, you can still compare them and say with a certain degree of confidence that yes, this is better than that. That's kind of my point.
Okay. So even so, it can still be argued though that just taking the first three sentences shouldn't be enough, or it can be better if you did.
Yeah, like I said, the whole pipeline could be better. But if your goal was to just show, is it comparable against state of the art, this is close, like not the best way to do it, but still good enough for some definition of it.
So I have a question. Have you researched so the previous state of the art? They have used the same representation one.
No. So what they did, so what they did was they actually performed the experiments using the state of the art package, which is available on GitHub as well, using their data. So they're not reporting other
so
accuracies. They're actually
same experiments with the previous.
Yes. So the previous state of the art, they run those experiments using the same data set.
But how did they build the representation of the previous research, or you haven't?
So the MMD critic, which is the state of the art, they just reported results on USPS datasets. They don't have the document comparison. And they also compare for, like, they're trying to find the best representative examples to train classifiers for. So they kind of report in the range of thousands of documents selected as opposed to 6 or 10 documents selected. So sort of different end goals, but still the state of the art for this particular set of problem. And you can sort of compare between the methods, if not like globally.
MMD critic solve exactly the same problem as
MMD critic is a prototype selection algorithm. Um, Prototype selection can be used for document classification, comparative document summarization, but it's not exactly the same problem. So prototype selection is basically saying I have too much data, I want to be able to build a classifier using it, but I don't want to use all of my data. Find me the points that I really need. Instead of doing dimensional reduction where you're reducing the number of features, you're kind of reducing the number of examples while maintaining a same level of accuracy.
in the graph that you showed, MMD critic was much lower in accuracy. So for all the different.
Yes. This one. So it's the orange one, I guess. It's the third from the left. So one thing to notice is that all of them have different levels of granularity. So for example, the first starts at 0.4 and goes up to 0.6. So the difference, even though it seems large because of the way it showed, it's actually like 0.6 points of accuracy. It's not that bad.
See in the bottom one for USPS,
Yeah.
MMD critic does really bad.
Yeah.
And so I didn't look at the MMD critic paper, but they mentioned in this one that it doesn't guarantee a set number of prototypes for each class, and so it's possible that it just doesn't have.
Do you mind repeating the point?
The point was MMD critic on the USPS data set, at least for the SVM classifier here, does significantly worse than the rest. And the authors in this paper mentioned that that algorithm has no guarantee of a set number of prototypes. At least that's what I read. So it's possible that it just like didn't find any prototypes for a certain class. And all the other data sets I think there were just 2 classes, right, divided by time, whereas USPS was 10, right, 10 digits. So that's why it shows up there and not the other ones.
Basically the MMD critic was done on USPS dataset, not.
Yes.
But then the results are horrible compared to.
So
how
like
come
I
that's the state of the
explained,
art?
right? So their primary target was prototype selection, and in the range of thousands of documents, not in the range of 5 or 10 documents. So that's one reason why it might be different. Why is it different? I honestly have no idea.
I mean, like, kind of like you're comparing results to well, not you, but like I mean the authors are comparing results to something that they know it's not gonna work.
It works pretty well for this problem.
No, I mean they know the MMD critic is not gonna work properly in that specific domain of a problem.
I guess that's one point, but like it might also have been that the authors just didn't know that it wouldn't work well for that few prototypes, and it's just still the best thing. It's still the best baseline they have. So.
I just have a question. Going back to, can you go back to your discussion point, please? The first slide. Yeah, so just this representation taking the title and the first 3 sentences. Did they give justification in the paper? Because I think you had mentioned on our call
Yes. So
maybe I missed this. The inverted triangle.
Inverted pyramid structure of news articles. So basically, most news articles are structured in this way. So they have a title. They have the first paragraph, which kind of describes the whole news article in brief, and then they go on to the rest of the document, which is diving into the details. So like. For example, let's say Golden State Warriors came back from 17 points down to win by 2. That's the first paragraph, and the next it's like they scored this much in this half, this much in that half, this much in that quarter. So that's so the idea is that most of the information should be in the first 3 sentences. And there was some paper from back in 1971, which was referenced in the paper we're discussing, which showed that the first 3 sentences had a significant amount of the information. Yeah. So.
But this is assuming that we're talking about news. documents.
Yeah, but all
The
the
data set
datasets
is
are
news articles.
collected
Okay.
from the tools.
Yeah.
Okay.
The data set is news articles.
Yeah, so they're pretty much saying we generally know this to be true. We can just save a bit on computation and sort of still prove our point.
Yes.
Okay.
Okay, makes sense.
Interesting.
Am I hearing myself? Okay. So I think another point that's useful over here is that their representation is they're using embeddings and they're just averaging things up. And using less of the text helps them not to overfit to the number of function words they have. So they would usually take over if you keep adding those together.
Yes.
I know in the legal space there's a lot of document discovery, especially when you have mergers and acquisitions. Like you'll have to do reconciliations, you'll have to go through and find all of the electronic documentation to reconcile and discover things that may have been missed by an auditor. Could this be applied to something like that, where you're going to go through hundreds of thousands of documents per se, and then only take the beginning to say, well, this document pertains to this type of situation, and it has some kind of monetary value attached to it, something like that?
So one of the assumptions that we make here is that the groups are somewhat defined. That
a classification problem, right? Of which group does this document belong to? It's like we know what the groups are.
Yeah,
we just want to find
they are pretty defined.
That represent them. What's the other way?
They represent them and find what are the difference between the two representation of the groups. So the groups should be already defined. Yeah.
Okay, I see what you mean.
Okay, so I was gonna say, so let's say you have a bunch of different people who shop at Loblaws and you have those clusters defined already, then you could use a method like this to find representative individuals from those clusters of people, or
theoretically, yes.
if you like treat their transactions as a document, maybe?
Theoretically, yes. We have to find a way to represent their purchases and preferences while making sure we don't break any privacy laws. The most important part.
What?
It was too young.
Okay, interesting.
Yeah.
How is the difference captured between two groups? I mean, this is one of the key contributions that
Yes.
we can distinguish between the two groups. So how is that represented?
Okay, sorry. Okay. Going back to the definition of MMD, we have MMD is basically capturing the difference between two probability distributions. So P and Q. Here we assume P is the probability distribution of the prototypes, and Q is the probability distribution of either the group it's from or all other groups. So the first thing that they're trying to do is they're trying to make sure that the like MMD, the discrepancy between the prototypes and the groups themselves from which the prototype is taken, that is low. So we have a negative of MMD squared of xg bar and xg. So this captures the similarity between the prototypes and the rest of the documents in that particular group. The second part of this equation is MMD xg bar and x naught g. So this captures the discrepancy between the prototypes of the group G selected and all other groups that are not G. So this is where they're capturing that difference. Yeah.
So basically we have two components here, the similarity and the diversity.
So that's
well, it's similarity and
Yeah.
discriminativeness.
Yeah.
yes, discrimination.
And then it turns out if you expand that term on the right, you get a couple terms that'll measure the diversity, which is how similar your prototypes in the particular group are to each other. And so they find a couple terms that if they take out a couple terms, they actually are optimizing more for diversity, like more for prototypes in their particular group to be far away from each other. So those are the three things you talked about at the start, is like coverage, diversity, which is all within a group, and then there's discriminatory, which is between groups.
Yes.
I'm just wondering if the authors have expanded on the possibility that how they defined the initial like categories or topics could really affect these.
That's actually a good point, because if the categories are really similar to each other, this method might suffer. So that's actually a good point. They should have considered that.
Yeah, I was thinking the same thing, because I would expect, like, over time, which is how they define their groups in the tests, like, I would expect a lot of overlap between documents in each group. So one of my discussion points was, like, it might be easier if you first looked for the documents that are most similar between groups and like filtered them out, because you're not getting a lot of information from those, right? You want to find the documents that are most different between the groups, if that makes sense.
So this means that each document should appear only once in a group, right? So you can't find the same document in multiple groups. But
Yes.
Yes, but you can have even similar documents, not the same.
But my question would be like,
because they have filtered it out. When they create the data sets, they create 3 data sets.
In the evaluation they did, each of the data sets were so different from each other that the problem of having the same document in multiple groups never arose. And even the USPS dataset, it's really well defined in classes. So whether or not that would actually be tackled or would work is your new research paper.
okay, so my question is around that anyway.
Any other comments or questions, arguments?
I just want to know how this USPS dataset can be used. I mean, I'm just, because news we know there is a topic about some, politics.
Is the question?
Can you repeat the question?
Is the question how is the USPS dataset represented?
Yeah.
Okay, so the USPS dataset is images of digits. So digits from 0 to 9, and they're represented in a 16 cross 16 image. So there's 16 pixels this way, 16 this way, so you have a square. It's basically like a 0 and 1, where 1 is for black, 0 is for white. It kind of like represents a digit. So it's really just numbers written out, and that's the data set. So what they do is they kind of run PCA on it to reduce the dimensionality from 256, which is like 16 squared, to 39. And they set the information content to 85. So like it's the top 39 dimensions in PCA retains 85% of all the information, and 15% is lost. And again, it's the same point about the data sets. Retaining all of the points might have had better results overall, but this is what you're comparing with. Yes.
So I have. What do you think that are some use cases so that all these methods can be applied?
So the most important
is the news.
Yes.
Like the trend of news, but other industry that can be applied.
So I think if not this, but a very similar example, like algorithm is used by Google News to group articles together and find which ones to show to us and which ones to show in the expanded list. Other examples, like they kind of show that this can be used decently well for prototype selection. So that might be an interesting thing to see using other data sets, whether it actually is good at prototype selection. Like there's like tons of data sets, you just run it on different data sets and classify and see if it works. Pretty much I think any problem which has a prototype selection issue with it, it can possibly be applied, or at least tested out to see if it works for that particular data set. Another thing it could possibly be applied for is like update summarization or storyline detection, because like we are finding diverse documents that represent the topic over time. So that's kind of the exact thing as storyline detection. Yeah.
Any other questions, comments? Going once, going twice. Okay, yeah, if not, then let's thank our speaker and thank our facilitators. And also our host, who